what's good? I'm really excited to start this new stream. I should really be studying right now for a test I have tomorrow, but things are looking pretty good. So I decided to kind of ditch it. I should be fine. And yeah, let's go ahead and start the stream. Let me just make sure that we are online. Cool. Everything's good to go. And it is up online. Awesome. I'm just going to share the link now, and then we're good to go. Okay, cool. Let's get started then. So, on the work that we did like 4 days ago, I believe now, I got really busy with some internship work, wrapping that up. But we were stuck on here. So we're moving on to dynamic self-information. And just to recap a little bit, we learned that hard prompt compression, which is really just pruning the prompt of low-level information tokens, is based off of the work of information theory, which essentially at its core can be summarized to be basically how rare a specific thing happens. And that's basically information, how rare something is compared to a set of things. In our case, it's a token which is being compared to a corpus of text. In this paper specifically, they used an offline corpus which consisted of articles within Wikipedia, ShareGPT. So it's a little bit outdated in the sense that ShareGPT does not exist anymore. GPT natively supports that feature. But nonetheless, the work is there and it's applicable. And archive articles like the one that I'm reading right now. But anyways, it takes all of this and basically it determines a surprise score, which is basically the information. And that is this formula here. This is the surprise formula. So even if I search up surprise formula, as you can see, I should get something like this. Yeah, see? Negative log 2 times p, negative log 2 times p to t. This is just a function that we're using, right? It might be of interest to just look at this in a little bit more context. So, could you explain this in a little bit more context? For reference, guys, my Claude has been taken over. I've used up all my limit for the day, so unfortunately I have to use this now. Nice. Okay. Right, so literally this is called self-information. So basically the work that the hard prompt compression relies on is off of Claude Shannon and specifically information theory. In the case of static self-information, it does not take into account the actual context that these tokens are a part of. So it treats each token as if it's the same, which, in language is not the best idea, because, a word could mean, or a token, I should say, could mean something very important, because of the context that it is in, but generally it's a low information token because it's so generally seen, and therefore it is removed from the actual prompt itself. But again, these are ways of basically slicing the size of the prompt. We got static self-information done. We first find the unigram frequency, which is basically how many times you see that token within the corpus of text, not within the text of the prompt, right? Within the corpus of text. So this is basically generalizing it to the wide general internet, right? Figuring out how many times this token is seen on the internet itself. And then now, once we know that, we can use that specific information within the Claude-Shannon formula and figure out the static self-information score, which is essentially how informative this token is, how rare this token is within that corpus of text. The higher the rarity, the more information, the more valuable, therefore it is kept in the prompt. If this is not the case, then it is removed from the prompt, but obviously that depends on the top K amount. K being the actual amount you want to keep. So K could be 200. That means you keep the top 200 tokens or the top 200 scoring tokens. And everything else below that 200 rank is removed. Okay? So that's a little bit of a very, very, 5-6 minute recap of the work that we've done so far. Now, dynamic self-information. This is where we bridge the gap in terms of the context, right? As I said before, the main problem with static self-information is that it is non-context aware. So what this does, dynamic self-information, is it captures context sensitive, as you can see, it captures context sensitive importance, right? And it does this through the form of using either an LLM or a scoring agent. So we're introducing some sort of transformer architecture which is able to handle context through the attention layers within it. So you need to understand a little bit about LLMs in terms of like the transformers, the attention mechanisms, stuff like that. Again, you don't need to really know all the math. I don't even know the math, but just understanding the high level fundamentals would be really, really nice. Right, so essentially what happens here is that when you're given a token T and its preceding context, right? So this means you could have, and I think I should use an Excel draw to really showcase this. I think that's a really good idea. Okay, cool. So let's say you have, where's text? Oh, there it is. Let's say you have this token. Let's say your token is cool, right? I don't know, something like that. So your token is cool. That is your T. Okay, that is your token T. Now your C, so actually like that, this is your token T. Now your C is going to be this. Let's say it is the Raptors are, and this is your C context C. Okay, so you have this token which comes directly after, I should probably make this a little bit lower, not too much, just a little bit, but you have this context which comes directly before the token, and this is what is being fed in the terms of C. And then you could just obtain a model probability and compute dynamic self-information. So this model probability is a metric which I'm actually unaware of. So let's actually search that up. And I guess I'll use Claude to help me out here. Sorry, ChatGPT. Model probability in the context of the screenshot I sent. And then I have to make a clear ask, so what is the model probability in the context of the screenshot I sent? And then I'll give a screenshot, which would just be this over here. let's see what happens. Yeah, I do know that. Okay, I think I have a rough understanding of what's happening. And before I even explain sort of what's happening in terms of, I guess, this architecture, you need to like have some sort of underlying understanding of actual LLMs, right? You need to understand what LLMs are and like how they operate. And I'm just gonna turn off my Wi-Fi here so that we can use Ethernet. So hopefully the stream gets a little bit better as we progress forward. Okay, cool. So, alright, let me just move down here. Okay, so basically what's happening is that we are first obtaining the model probability, and we're using that to compute self-information, because remember that the self-information or the information formula, which is just this, requires probability. That's probability right there, right? So if we just calculate the model probability from the actual LLM and we plug it into there, now we have a context-aware probability, right? Because when the LLM creates a probability distribution, I'm going to explain what this is, but I'm first going to explain in terms of like this, if you already know what LLMs are. But anyways, going back to my train of thought, when you have a probability distribution which is generated from first the raw scores, which is just the logits from the transformer, and then using a softmax function, they're actually turned into the probability distribution, you know basically the most probable tokens, right? So you have a slice, you can think of it, of 100. And from that, again, I'm just making this up, 50% of it could be, the probability could be, I don't know, Paris, right? 40% of it could be Berlin. And 10% can be Delhi, India, right? Very improbable that it'll actually be Delhi, India. Again, it doesn't necessarily need to be cities. It could be any word or any chunk of a word, because a token is not just a word, right? It is basically the most granular form of unit that an LLM understands. And it could be any string of text, right? Even it doesn't necessarily even have to be text, right? In multi-model systems, it could be pixels, right? But when you're looking at images and stuff, that's tokens. But that's why I like to think about it as just the most smallest form of unit that a LLM or an AI system at large can understand. But anyways, in the case of LLMs, obviously it's just text. So now, before I ramble there, what we're essentially doing is a transformer. So now I'm going to explain just transformers. But a transformer, and I learned this quite a while back, like 12 months ago. But a transformer basically creates a probability distribution of all possible tokens given preceding token. Sorry, a preceding set of tokens. So, for example, this is your preceding set of tokens, which acts as your context because it's underlying information which fuels decisions for this specific token, right? And what the transformer will do, right? So let me actually just move this stuff up here. What the transformer will actually do is it will take all of this. It'll be like, okay, cool. I understand the context. I understand this, right? And it will actually build a probability distribution, right? So it'll build a probability distribution. And what this means is that given a set of tokens, figure out how probable that token is to be the next token. So within that set, there's obviously going to be cool, but there's going to be another different sets of tokens or different sets of text as well. So you could have something like, I don't know, cool, or fun, or better. Sorry about that. Alright, cool. Okay. So, now, where was I? Okay, yeah, so creating a probability distribution. So, let's pretend there's these three different tokens, right? Obviously, in a real model, there's going to be multiple different tokens which have a probability distributions, but for, mental models, let's say it's just these three. So remember, this is your context. We forget about this, right? So just pretend that you have this context, and then based off of that, the transformer does some work, and it builds a probability distribution which dictates that cool is 80% probable, fun is 15% probable, and better is 5% probable, right? When you add this up, it'll be 100%. 95 plus 5, 100. Now, that means that the most likely token is cool. But fun fact, in an actual LLM, they don't always use the most probable token. They actually use a random set of the most the most top ranked tokens. So for example, if I had cool be, 40%, and this be 35% instead, and this taking the rest, right? But if I had something like this, well, then both of these are pretty much the same in probability, so the model would sort of pick, right? It'd be like, should I do cool or fun, right? And it would just randomly select which one it should do, or which one it should pick, right? But in our case, let's just say it's this. So anyways, the transformer figures this out within the LLM. Remember, transformer is the underlying architecture within an LLM, right? It's the underlying architecture neural network which just mimics the capabilities of humans in some way, and that's what is served as a foundation for the AIs that you use, like GPT, Gemini, Claude, DeepSeek, the more open source ones as well, like Kimi, right? But anyways, this is what you get, right? Now, what CompactPrompt does, or specifically dynamic self-information, is that it basically finds the probability, the probability of a specific target token. In our case, that was cool, which was 80%. So then that probability is what we yeet into the self-information scoring mechanism and figure out the dynamic self-information, because now this is basically telling us the probability in terms of the context which was previously given. And obviously this whole architecture, this arrow, basically is like a very complex process, right? It includes so much more that I'm just abstracting away because we frankly don't need to know that part, right? What you need to know is that you have this transformer, and then this transformer, which is the underlying architecture of these LLMs, basically take a set of tokens as context. And based off of that, they're able to build a probability distribution, which is essentially how probable a set of tokens are. And all of those probability scores add up to 100, right? So in this case, we had a distribution of 3 tokens. They all add up to 100, right? And based off of the target token of T, we figure out the probability percentage, and that's what we plug into Claude Shannon's surprise formula to figure out the dynamic self-information. And then it's the same process as static self-information in that we rank the most informative tokens and then the least informative tokens, figure out our top K amount, and then remove anything below top K. That's it. But in this case, since we're employing these transformers and these context-aware systems, because of that, you now have a context-aware process where if one token, for example, is super relevant, super duper duper important to, one specific part, right? One specific chunk of the text due to the context preceding it. This system takes that into account. Obviously, it's more expensive now, though, because now you can't just have, this deterministic flow. I mean, it's still deterministic, but what I mean is you can't have this, very independent flow where you're not really relying on third-party systems. Now, you need to use a pre-trained LLM, right? You're not going to go and train your own LLM. That would take billions of data points and millions of dollars to even get a working crappy LLM, right? So you're obviously going to be employing some sort of LLM from a service provider like OpenAI or Claude, and that is not cheap, even with with the $20 plan, right? It scales up as you use this more often. Eventually, you're gonna have to definitely go into the API plans for sure. So because of that, yeah, it's the trade-off is you obviously get a much more accurate system with dynamic self-information, but now you're relying on third-party tooling because you need that pre-trained LLM and that transformer architecture to actually capture the context and use it within your hard prompt compression or pruning, right? And in the case of CompactPrompt, it actually uses both. It uses the dynamic and static self-information mechanisms to figure out what tokens it should remove. And we're going to look at that very, very soon. I just have to use the washroom really quickly. Once I do that, we'll go through another review of dynamic self-information, making sure that we really understand that. And then we'll go into the cool blend that CompactPrompt actually proposes. Okay, I am back. Alright, cool. Let's move on then. Okay, so dynamic self-information, very quickly, it allows us to capture context-sensitive importance, which makes it much more relevant and more accurate when we're doing hard prompt pruning, because now we're not treating each token the same. We're actually using the context that precedes it to actually understand if it is really important to keep this specific token and not remove it, right? And that happens through a pre-trained LLM or scoring agent, both of which have some sort of transformer architecture, which essentially has these attention layers which are able to capture context. And because of that, what happens is it builds a model probability. Okay, so it builds a probability distribution, I should say. That transformer builds this probability distribution, which is essentially a set of all tokens and basically a probability score given to them. And when you add all of those scores, you should get 100%. All right. And when you're given a token T, which is your target token, you're going to essentially find that within the distribution and use the probability score allotted to it. And that is then plugged into the actual self-information formula that Claude Shannon cooked up. And that will give us the dynamic self-information score, which then we use the same as a static self-information score in the terms of ranking and removing the tokens in terms of top K prompts, right? And so again, as it says, this score reflects the novel information contributed by T in its specific prompt context, complementing the corpus level view, right? Because in the case of static self-information, we're using a corpus, right? We're using a large corpus of text, this huge collection of text, and we're comparing that token to that huge collection of text, which means we're only getting a general relativity as to how informative or how rare or how important that token is to the specific prompt, right? We're not getting a really good view in terms of the unique constraints that that prompt might have. But in the case of dynamic self-information, we're using this pre-trained LLM, right? It's trained on the world's data already, so there's no need to collect this corpus of Wikipedia, shared GPT conversations, or archive articles. None of that, right? It's all already taken care by the pre-trained LLM. All you need is to basically just have that prompt, and you target a specific token, and the LLM, using its transformer model or architecture, is able to figure out the preceding context of C, which is all the tokens or a set of tokens that happen before, the position that token T will take. And based off of that specific context, you build a probability distribution using raw logits, and then that is basically put into a softmax function to build this probability distribution. And that is essentially a set of tokens, which again add up to give us 100, and we basically just take the token which we're looking at within that specific probability spread, and then we take that probability score, plug it into the self-information formula, because that's universal, right? This is not exclusive. This specific formula here is not exclusive to static self-information. It is just the general self-information formula. So that's what we use to figure out how informative the token is within the dynamic sense. Because now, because of the LLM, we actually took into account the context, right, that specific token within its specific position lived in. So that's a beauty. But again, there are trade-offs, and as an engineer, you should know these trade-offs. In the case of dynamic self-information, more costly, because now you're relying on pre-trained LLMs, which don't come for free, right? Even if you use something like an open source model, you need like pretty good hardware to run it, right? So you probably need to invest in like a MacBook Pro at least. Like a MacBook Air would not cut it for at least a very good LLM in the case of enterprise applications. So definitely you need a lot of more capital when you're using dynamic self-information. That's not really the case for static self-information, right? Because you're really just using a for loop. It's just a glorified for loop, right? The unigram frequency is a for loop which goes through the occurrences of a token and basically is able to compute how many times it does that and then provides a percentage off of that, and that is what we plug into the formula itself, right? So not that much compute, and it's really easy to implement by yourself. You don't need like a service to do that. You don't need a third-party service, right? So static self-information, cheaper but less accurate because it's not context aware. Dynamic self-information, more expensive due to dependence on third-party softwares, but way more accurate because now it's able to capture context, which is really, really important. Now, let's look at their innovative approach, CompactPrompt's innovative approach, which involves basically blending both static and dynamic self-information. All right, so this is really, really sick. And yeah, let's see it. Okay, cool. Combine scoring and phrase level pruning. We integrate static and dynamic measures through a weighted combination strategy, employing a simple arithmetic mean when both scores exhibit less than 10% relative difference, as shown in the formula below. So this is the formula. Honestly, it doesn't look too bad. It's a very simple, I believe, way of going about it. Let me actually see here. Interesting. So in this case, we are essentially using both static self-information and dynamic self-information, and we're doing a double score where we're basically taking, a piece of token, and that token is fed into the static self-information process and the dynamic self-information process, and then based off of that, we are basically finding the relative difference first. So that's what this is doing here. This first formula is basically figuring out how far apart are these two scores compared to the static one, right? Because we're dividing it by the static. Okay. Okay, I'm reading through this, and I actually have a couple of concerns which I think should be addressed. This is what happens when you active read. You should always not just take everything at face value. Okay, my voice agent's working. I have a bit of a confusion. Why exactly would we do both a self-information and dynamic information process? Wouldn't that just lead to more cost in the long term? And isn't it sort of like what exactly is the benefit in using both scores and basically figuring out the relative difference? And based off of that, we can basically determine whether the static self-information score is reliable or the dynamic self-information score should be used. Wouldn't it be better to figure out some sort of way where we could use either or depending on a constraint of problems or constraints of factors? right? Cheap, computed, stable. Right, because Apple in this case is not meaning the apple that we eat. It's meaning Apple in the case of the company. I mean, this is just one part of the paper, but that is interesting. When did this paper come out, actually? It came out like 7 months ago, basically. I can say confidently. So basically, they are using both scores as sort of a confidence check. We're basically seeing how much of a difference there is between the dynamic score and the static self-information score. And then if there isn't a big difference, then we take the mean of it. But if there is a very big difference, then we just take the dynamic self-information score because that's more reliable. That makes sense, and I could get why that works, because in that case, you're basically double checking to make sure that your static self information score is good, and that gives you the more general context, because it's not context aware, it uses the large corpus of text. So, sure, I could get behind that, but I'm really confused on why there's even a need to use both approaches. Wouldn't it be better, excuse me, to just use like one of them? Like for example, like as you said, using the static self-information one first because it's really cheap, and then depending on the score and the confidence level of that technique, we can switch to using dynamic self-information. There's an obvious flaw to that I just realized, because sometimes the confidence score could hallucinate, and when something is definitely not supposed to be removed, it gives a high confidence of it being low informative, so then we remove it, even though the dynamic self-information score would not have done that. So okay, fine. I guess in that case, this approach would work out, but it's just that computing both static and dynamic self-information just seems robust and like not really needed per se, or redundant, not robust but redundant. Nice, I earned another free day. Let's go. Just pick one, breaks in practice. Static for skating, your idea. Use static and only call dynamic if needed. The problem isn't just hallucinated confidence, it's systematic blind spots. Static scores are built from global statistics, so they consistently miss contextual pivots, not accept negations. Named entities in rare contexts. Named entities are just people that are named, or named things, right? Yeah, to roll out phrases and types that act as proper. So basically just proper pronouns, which are referencing to specific things. Task specific importance. So in instructions, for example, okay, here's a catch. These tokens often look unimportant statically, so your game never triggers dynamic. You silently drop critical tokens. This is the noise. Spies errors. Fix that. Denying a higher cost, more variance. Occasional overweighting of your tokens. Okay, but then in this case, why exactly do we even need the static self-information at all? Why not just use dynamic self-information for all of the majority? Oops. But then why are we using self-information in the static mechanism at all? Why not just use dynamic self-information? I think a better question to understand what I want to understand is why exactly is this pipeline or this framework called CompactPrompt using the mean of the dynamic uh, and static self-information score as a way of figuring out the final self-information score, which we're going to be using to do the hard prompt pruning, if the relative difference is below 10%, which means they're practically the same. Why exactly is it using the mean then? Okay. Good question. You're right to zoom into that you told because mean isn't arbitrary. He's doing a specific job. First, what does delta less than equals 0.1 really imply? This says the two scores are close enough that they're effectively measuring the same thing. So now you have two noisy estimates of the same underlying quantity, true importance of this token. Why take the mean? Because when the two independent estimates agree, the best simple thing you can do is average them to reduce the noise. This comes from basic estimation theory. If you have two unbiased estimates with noise, the average has a lower variance than either one alone. There's more math involved now. Very nice. What exactly is noise? Is it just irrelevance or a little bit of inaccuracy within the probability metrics, or the, I should say, the self-information score built due to irrelevant stuffs? So like you can think about it as like a rounding error when you're doing some math. You know, for example, you could have like a really long number, maybe an irrational number, when you're doing some calculations, and so you just put 7.56 instead of 7.566666 ongoing, right? And that introduces a noise because it's a random error that happened due to the rounding. So essentially, it's these random, unpredicted errors that happen due to unprecedented factors when the calculations were occurring. Okay. Right, because in the case of the 7.566666 ongoing, you'll never be able to truly reach the most accurate amount. There will always be some level of noise because of the fact that those sixes are ongoing, which means that there is always going to be an, uncontrolled, you should say, error within your calculations because of the factor that you have this irrational number within your calculations. I love these voice agents, honestly, because they just make things so much easier for me. Okay, so there's something that's wrong. Oh, okay, yeah, that's what I mean. Well, yeah, that's what I mean. I mean, when you're actually going to write down that value, right? Uh, you're not necessarily going to write it as 7.566666 ongoing. That's physically impossible. You can't figure out the end value of an irrational number, right? So there always has to be some sort of approximation which occurs, which is what the noise is, right? There always has to be a point where you're like, you know what, I have to stop, right? I have to stop, so that I can continue on with the calculations, and that is the unprecedented or uncontrolled error that's happened. So I think maybe using the example of rounding error might be a bad idea because it's not necessarily fully reflective of what noise is. What would be an analogy that you would use to help me understand what noise is at a much better scale? Because I have a general rough understanding from the work that I've done before, but I've never actually bothered to define it properly. From my understanding right now, textbook understanding, a a noise is basically uncontrolled error that happens due to some sort of factors. And because of that, there is just a little bit of variance in your final calculation, which doesn't reflect the true value of the actual calculation that you're doing, right? So in the case of the information, that would mean having a small deviation or small error, which means that the actual importance is something else compared to what you've calculated, but it's very, very minuscule. But by taking the median, or sorry, the mean, with both scores, we reduce that noise. Cool. So we get it almost. We're almost there. I see, and these are the three different mathematical errors that can happen. In our case, we're looking at noise, which is random variation, meaning random changes which occur within your calculation, which leads to a different answer compared to the real answer. In the case of bias, that is some sort of skew within the work that you're doing. That doesn't really matter in our case, so I'm going to just skip it. Approximation is what I was talking about before. So noise isn't necessarily an error in the sense that like it's wrong because of some sort of calculation process, but rather it is an error because of a random variation that happens due to uncontrolled factors within your calculation. That could be within the LLM doing something that's a little bit different, or the some sort of issue within the calculation of the static self information. It's stuff that we cannot handle and we do not know, but there is a little bit of that noise. Now, by taking the mean of both those values, we're basically making the self information score much more accurate, because now this noise cancels out a bit, because if there was noise in one specific aspect from the dynamic self information and another aspect from the from the static self information, well then now they both cancel each other out. Oh, I see what you mean now. I get it. It's clicked. So in the case of the noise, right? I like to think about it as chemistry right now. I'm using the Avogadro's number, which is 6.02 times 10 to the power of 23 moles. Right now, that is a model which we use to determine the amount of particles within a specific substance, but it is just a model, which means there is going to be some sort of noise. There's going to be some sort of random variance within the calculations that I make, because it is not necessary for every single mole within a specific substance to have exactly 6.02 times 10 to the power of 23. And in fact, there would also be an approximation error because of the fact that I approximated that value. But either way, there's going to be that random variance due to the fact that I'm modeling the amount of particles with Avogadro's number, which is imperfect modeling. And essentially every model that we make is imperfect in some way, because it cannot take into account every single factor that's happening within the real world. And that's why the noise exists. Oh wow, so literally every single mole has exactly 6.0 whatever 2 times 10 to the power 23 moles. Is that an approximate value or imperfect modeling? I see. Okay, that was just me not knowing chemistry properly. Um, Cooked. But anyways, okay, but I guess in that case, as you said, the measurement would be imperfect modeling because there's obviously going to be some sort of external factor which leads to random variance, and that is your noise. Random things that happen which reduces the accuracy of the actual number, the true number of your calculation. So when you have an imperfect model, it leads to a bias. Mm. I understand. So my statement is true, but with nuance. When the model misses something conceptually in its modeling, then that leads to bias. But if it is taking in some inputs and those inputs are flawed due to external circumstances, that leads to the random variance within the final estimate that you make, which is noise. And in the case of approximation, that would be when, in your model you're rounding something, which leads to some sort of error because now every other value takes on the approximated value instead of the true value. Oh, so in physics, there's a lot of bias in the calculations that we make because we make a lot of simplifications, like assuming no friction. So that would be a really good example. When we model a problem to assume no friction, even though there is friction there, it might be just negligible, so we just forget about it because in practicality, it doesn't really matter. But that leads to a bias, which means that our all of these errors lead to lower accuracy of the true value. But in the case of bias, or in the case of any of the errors, it's just different ways of getting to that imperfectness. In the case of bias, it would be because you miss something systematically, right? You miss something in the model that doesn't really depict reality. And in that case of the systematic simplification of physics, you're just removing friction from the equation, even though it's there. Now, in the case of noise, that's random variations within your estimate. So, this means that, so this means that when you have factors which are variable or unstable, right? And because of that, these factors, by the way, influence the calculations. So it could be like inputs or outputs, and there is some sort of imperfection from them due to this unreliability or unstableness. And because of that, there's going to be a little bit of random variation within your estimate. So you should be getting the same answer over and over again, but you get a little bit of a wrong answer in the terms of not getting necessarily the true value. And approximation is just an error from not having the precision be correct due to rounding it or approximating it. Cool. I mean, I told it to be brutal with me, so if it gave me this sort of answer, that means we're doing pretty good. Your physics example is perfect. Awesome. Bias doesn't just lower accuracy, pushes results into a predictable direction. Okay. Only for more great use of true, but the beautiful. I see, but in the case of my compact prompts, and now going back to AI infrastructure, we are only taking the mean or average of both scores, which means that we're only fixing the noise issue. So where exactly is bias being presented or fixed, right? Because I would assume bias would come from the first one, self-information, because we are modeling with some simplification. We're not modeling with the context or the related information of that token. So we're just assuming that all tokens are treated the same, which is a fundamental flaw in the model, which creates that bias. So there's that bias, but when we're using the mean, how exactly are we solving the bias of the static self information and the noise from the LLM because of the fact that you're using these transformers models, which are dynamic systems, so there will be some sort of random variance. Right. So the second step is where bias or an understanding of bias comes into play a lot. Interesting. Interesting. On an intuitive level, though, I still don't quite, or I still haven't quite internalized why exactly taking the mean or the average of both the static and dynamic will reduce the noise that comes from both. Because now I understand why exactly we're doing this, and it makes sense, right? You need to understand some foundational mathematics, which I get now, but we're basically trying to remove errors within the self-information scores that are being produced. And so the first one that we try to remove is noise, and that can only happen if static and dynamic are roughly the same. And the way we do that is through the mean. Now, if they're very different, that means static is very biased, right? Because it has that fundamental flaw of simplifying everything, all tokens to be treated the same, which means that our mathematical modeling is imperfect, right? And so in that case, we would just use the dynamic so that the dynamic score, so that we're just fixing that bias automatically, right? This makes sense, but what I don't understand is in the case of noise, how exactly are we using the average or the mean between both of them to remove a lot of the noise? Because in the case of the second part, where if they're very different, well then you're obviously not going to use a static one because it's very biased due to its imperfect modeling. So then just use a dynamic because it is fine tuned in the case of being context aware. Oh wow, it was over here. Okay, we'll read this as well. I did not see that. Nice, nice. But chat got me, so that's pretty sick. Um, I'll read through this a little bit as well. Uh, but I'm pretty done for the day, so I'm probably just gonna read one paragraph, maybe quite like very roughly understand it, and then we will tackle this another day. Hopefully, uh, day after tomorrow. I have a test tomorrow that I actually really need to lock in for. But we'll see. We'll see how the wind goes. Okay, so I understand this now. Basically, these errors or these noises which are occurring between both of these specific uh, scores are somewhat independent of one another, and because of that, when you take the average of them, they might fully cancel out or partially cancel out, which leads to a reduced amount of noise. So the actual the actual goal of doing this blended approach of using both static and dynamic self information is not to fully remove noise from them, but at least reduce the amount of noise so that you have a somewhat more accurate self information score that you can use within your tokens. That obviously means more cost because now you have a more overhead, because now you not only have to worry about self information systems, static self information systems, but also dynamic self information systems, and vice versa if you had implemented dynamic first. But it's very worth it because you could reduce a lot of the noise, and the noise is a huge problem. So it's basically they're different enough in the sense that they're not directly correlated to one another because static errors come from global systems like corpus text, whereas dynamic errors come from local systems, which is the context that they live in. And that's obviously mixed with the global system because the LLMs are pre-trained, but it is context aware, so it's fine-tuned for the specific context that you know the target token is part of. I was just like iffy wording. I don't mean like fine tuning in the sense of like model fine tuning, but it's apt or it's adapted for specific context. Okay, but I know that, so I think that's fine. I'm just gonna skip over this because this I already know. Using the probability distribution in the self information formula to figure out the dynamic context. That's all well and good. Cool, 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 cool. Okay. The reasoning behind 10% threshold is because lower, for example, 5% or higher, 15% cutoff, till too far forward one method, either over favoring dynamic noise or underreacting to true context changes. 10% offers a pragmatic compromise. When both models produce similar scores, their average provides a stable estimate that benefits from both corpus level statistics and contextual information. So basically a hybrid and a blend of both. That's what we're getting at here. However, when scores differ significantly, the dynamic method's ability to capture context-sensitive importance through querying the pre-trained model at runtime is more reliable than the static corpus statistics. So that's in worst-case scenarios when they're not roughly the same, the scores. So in that case, hey, we're going to use the dynamic self-information because that's obviously more accurate due to it being context-aware. rather than being the global sort of context from the corpus text. Cool, 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 cool. Okay, so maybe a quick wrap up is in order, and then I'm just gonna just read through this. I'm not really gonna give too many insights because I'm trying to go to sleep. But yeah, looks pretty good. Okay. In conclusion, hard prompt compression essentially allows you to rank these tokens based off of a scoring system. We knew this from the beginning, but now we know exactly how this system works at a low level. It uses basically information theory, which is essentially how informative or how rare a token is given a specific set of tokens, right? And so there's two different approaches that you can take: static self-information and dynamic self-information. Static self-information is not context-aware, whereas dynamic self-information is context-aware. Static self-information uses unigram frequencies, which is essentially how many times a token occurs within a large corpus of text, and it plugs that into, based off of, getting a percentage, it plugs that into the static self-information score formula, which is what Claude Shannon, the mathematician behind information theory, had cooked up. The dynamic self-information scoring uses the same formula, but instead of using unigram frequency as input into that formula, it actually uses a model probability, which comes from the probability distribution that a transformer cooks up based off of the preceding context and the actual token within that distribution. And that distribution is essentially figuring out which tokens are most probable to be the next token given the preceding context. Now, combined scoring and phrase level pruning is what this paper is proposing. It is a way of reducing the amount of noise that you have within your actual within your scores, which is just the random variances that occurred during the calculation of the static and dynamic self-information processes. And that happens by first figuring out the relative difference. This is basically figuring out if the two scores, the static and dynamic self-information for a specific token, are relatively the same. And if they are, then we take that score, then we take those two tokens, those two scores. Yes, we take those two scores and we find the mean. Because once we find the mean, we're essentially at least partially canceling out the differences between the two, right? Between the two errors within dynamic and static self-information, right? And what that does for us is it basically allows us to reduce the overall noise of the final score. However, if both of the scores are heavily unrelated, like they don't make sense, both of them are completely out of the world, and that is exhibited by a more than 10% difference. And this comes from research that they did, this 10% number, this 10% figure. If that is the case, well, then we're just going to use the dynamic self-information score, because that is much more reliable compared to the static self-information score, due to the fact that it is context aware because of the transformer architectures that we're using. All right. Okay. So then now let's move on to the next part, which is textual n-gram abbreviation. So this is actually going into not just the prompts, but the external data attachments, which are within the context windows of your AI systems, right? So n-gram abbreviation uses a method similar to LZW, Lempel-Ziv-Welch algorithm, that compresses text by losslessly replacing common sequences with short human-readable tokens. Losslessly, as the name implies, means that we're not losing anything. In the case of hard prompt compression, we were losing the tokens because there was nothing to replace them. In this case, we're replacing n amount of consecutive, tokens with abbreviations that are human-readable. So you can search, index, or apply natural language processing (NLP) directly on the stream without full decompression. It delivers substantial size reduction with simple table lookup encoding, more transparent and lightweight than heavy binary compression like zip or bzip2, and reversible, unlike lossy embedding, at minimal compute costs. So that's basically just saying that there's a huge benefit in the case of reducing the amount of size of the actual data, and also on top of that is reversible because it's losslessly, right? Which means that if you did not want this change to apply, maybe you don't want to see the abbreviations anymore, with very little compute costs, you can reverse these abbreviations, and now you have, you know, the actual data file again from the beginning. To compress attached text, we employ a user configurable ngram abbreviation pipeline, and then it goes into the actual pipeline that it uses. I'm not going to get into that. I'm just going to leave it here for now. We learned a lot. There's a lot of information overload, so I don't want to, you know, abuse my brain even more, I guess. But it was really, really nice to do this. I find this to be really good exercise for critical thinking as well. You know, your brain is a muscle, right? You want to use it and exercise it. And by doing this, I find that I'm critically thinking a lot and really using that brain power that I should be. So definitely going to be reading more research papers and figuring out ways that I can integrate it into Next Voters. This is definitely going into Next Voters because there's a lot of system prompts that I'm using. So I'm thinking of building a pipeline where I literally do hard prompt pruning automated. Right, so I run my prompt that I get, you know, I generate it usually myself, and then I ask Claude to refine it, and then I push it through this actual pipeline which I'll build from the insights of this paper, and then that is the final system prompt which the agent sees. So I'm really excited to actually document that process. But that is the design that I'm thinking of. A separate pipeline on a separate repository, which is just like a simple Python file, which I run, and then I can input the system prompt, and then it uses the logic from this paper to actually like improve it, right? To actually improve, or I should say reduce the prompt size. So yeah. I'm really excited to implement that once I'm finished with this paper. Not too much left because it's just this much, right? I'm not really going to go into a lot of this part. I think they actually have their own CompactPrompt SDK, I believe. So if that is the case, I might just use theirs, but understanding it might be really nice because there are different places where I might want to do a little bit of tweaking. But yeah, definitely I will build a pipeline for just hard prompt compression by itself, right? When I want to build new system prompts for different agents that I'm making or different LLM calls that I'm building. But yeah, okay, that is it for today. I think I'm pretty tired, so I'm probably gonna go to sleep now. But bye.